Limits, notation, graphical and numerical analysis, and one-sided limits. Our objective in this lesson is to investigate a limit using a graph and a table. Let's start off with what is a limit? If f of x becomes arbitrarily close to a single number L as x approaches c from either side, either meaning both sides, then the limit of f of x as x approaches c is L. In simpler terms, a limit is where a function is going, where it's headed, what is its path, where a function is going, not where it gets. It might never get somewhere. It's all about where the function is going. What is the function getting close to? Not what does it equal. What is it getting close to? Not what does it equal. Now, notation, we see this notation. The limit as x approaches c of f of x equals L. It's important we know how to say that verbally. The limit as x approaches c of f of x is equal to the number L, or is equal to L. We also have one-sided limits. For one-sided limits, we could have the left-hand limit. That would be for all x values less than c. Notice that notation right there with that little negative symbol, meaning coming from where the negative numbers would be on the left. This is the limit as x approaches c from the left of f of x is equal to the limit on the left. And then, of course, we have the right-hand limit. Those are for values of x greater than c. That's the limit as x approaches c from the right. See that little plus sign like an exponent of f of x equals the limit from the right. And we say the limit as x approaches c from the right of f of x is equal to the limit from the right. So graphically, observing this graph, notice that if we want to observe what is the limit as x approaches c is the x value we're usually going to. In this picture, let's label that as 2. It's 2 units from the y-axis, and L as 3 units above the x-axis. So the limit as x approaches 2 of our function, we'll label this function f of x so that it is clear, of f of x equals, so I notice that coming from the left side, the function looks like it's getting closer to the y value 3, and coming from the right side. So when I say the left and the right, I'm thinking on the x-axis, coming from the left and coming from the right. Coming from the left side and coming from the right side, both sides approach the y value 3. Now I want you to notice that at that x value 2, there is no function value. So while f of 2 does not exist, DNE for short, f of 2 does not exist, the limit as x approaches 2 of f of x does exist because it's all about where the function is going. Now, numerically, when we observe a table of values, we're looking at values coming from the left side of 2, see getting closer and closer to 2, starting with something that's close to 2, like 1.97, and getting closer, 1.99, and then 1.99. So these are coming from the left side of 2 versus looking at the right-hand limit where we're getting closer to 2, coming from the right side of 2. So see, we start with 2.1, and then 2.01. So we start close to 2, and then we get even closer, and then 2.001. And evaluating our function shows us where these function values are going. So looking at these y values, 2.6, 2.89, 2.97, where does it look like these function values are going? We see that at 2, the function value does not exist. But what about where the function is going? Looking from the right side of 2, 3.5 is what we get, and then 3.33, and then 3.12. What are these values getting closer to? It looks like both sides are getting closer to the y value 3. So using a table of values, we can observe that the limit as x approaches 2 of f of x equals 3. Noticing what happens from the left side of that x value and from the right side of that x value. Notice that we were able to observe values in both of these situations. Please note that if there is no single number that the value of f approaches as x gets closer to c, we say that f has no limit as x approaches c, or the limit of f does not exist. That's important. That takes us to this theorem that the limit L of a function y equals f of x as x approaches a number c exists if and only if both one-sided limits exist at c and both one-sided limits are equal. Using our notation, that means the limit as x approaches c of f of x equals L if and only if the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right, which equals a number L. Let's take a look at the following types of functions who have limits that do not exist. For these specific functions, the limit as x approaches 0 of f of x does not exist. First situation, the function approaches a different number from the left side of c than from the right. Notice that coming from the left side of c, it looks like the function is headed towards 0. Coming from the right side of c, it looks like the function is headed towards 1. We would write the limit as x approaches 0 from the left of f of x does not equal the limit as x approaches 0 from the right of f of x, because this value is 0, which is not equal to the value of the limit coming from the right, which is 1. Therefore, once again, the limit as x approaches 0 of f of x does not exist. Another type of function is when the function increases or decreases without bound as x approaches c, such as in this rational function. This has a vertical asymptote at x equals 0. A vertical asymptote is where you'll find one of these scenarios. And finally, the function oscillates between two fixed values as x approaches c, such as in this picture. It is not clear where this function is headed as we get closer to x approaching 0. No clue. We could observe a table of values and we would see that the values keep going up and down. Let's take a look at some examples. For this example, we'll want our graphing calculator. Complete the table and investigate the limit. We are going to evaluate the limit as x approaches -3 of the rational function 2x squared plus 7x plus 3 over x plus 3. Since we are looking what's happening as x is approaching -3, we're putting -3 in the middle, and we are going to explore values from the left side of -3, and we are going to explore values from the right side of -3. If we go to our graphing calculator, We are going to plug in our function, alpha y equals, enter, and we will type in 2x squared plus 7x plus 3 down to type x plus 3. We will go to our table set, and we want to make it ask us for the independent variable. Then we go second table, and notice there is nothing in there, and we type in the values we need. Negative 3.1, enter. Notice it puts the values in there. I notice that it's a fraction, and perhaps I want to change the mode so that I get it to be a decimal, and I can go to answers and decimal. Enter. Let's see if that helps. There we go. And sometimes I do want fractions, so we may have to be careful with what we do there. And so on and so forth, negative 3.001. And we type all the values that we need, negative 2.999. Now sometimes we might need to round, in which case we would always round to at least 3 decimal places. So we'd finish filling in that table and then write those values in and explore what happens. So coming from the left, we were noticing these values, and we plug them in, and we see that coming from the left, it looks like these values are approaching the function value 5. How about coming from the right? The values that we plug in yield negative 4.8 on that side, negative 4.98, negative 4.998. So coming from the right side also looks like it's approaching 5. Now if I go back to my calculator and I actually type in the y value, or the x value, excuse me, negative 3, you'll notice it says error because there is no function value at negative 3. So we do see here that the limit of our function equals negative 5, even though the function value at negative 3 does not exist. Let's take a look at one more example. We are going to use the graph of g of x shown to evaluate the following. What is g of negative 4? To see that, I'm going to go to where negative 4 is, and I'm going to see where the point on the graph is, and that's at 1, 2, 3, 4, 5. Negative 5 is what that value equals. Now I'm going to explore the limits as x approaches negative 4. This right there means from the left. Coming from the left, I'm going to see that the function is approaching the function value, which is also negative 5. This one shows coming from, because of that plus sign, the right of negative 4. So I'm going to be looking at the other path coming from the right. Notice that's going to a different y value. That's going to the y value 2. So that limit is 2. And notice since the left-sided limit and the right-sided limit are different, the limit as x approaches negative 4 of g of x does not exist. Notice I am not putting an equal sign because d and e is not a number. Does not exist. Let's take a look at g of 0. G of 0. There is a point there, and that looks like the value negative 4 is what the function value. Remember, these right here, these 3 mean the function values. whereas these are the limits, the limit from the left and the limit from the right. Notice both sides are going to the same value, -4. Therefore, the limit as x approaches 0 of g of x is also equal to -4 because both of these are matching. Finally, g of 3. 1, 2, 3. Here's the x value, 3. I look down and I see, I look up, I look down, I see nothing. There is a hole, therefore g of 3 does not exist. Does not exist. Feel free to write it out if you want to, as long as you don't put equals. As x approaches 3 from the right, be careful, mixed it up this time, coming from the right, it is going somewhere, even though it never gets there. It's going to the y value, -2, and coming from the left, also going to -2. Therefore, because these are the same, the limit as x approaches 3 of g of x is -2. I hope you had fun today. Thanks for watching.